Hi, students. In this lecture, I am going to discuss problems based on collisions. Let us see. Right, see the question given. A rod AB of mass m and length L is lying on a horizontal frictionless surface. A particle of mass m traveling along the surface hits the end A of the rod with a velocity V0 in a direction perpendicular to AB. The collision is elastic. After the collision, the particle comes to rest. Find the ratio. Small m by capital. Point P on the rod is at rest immediately after collision. Find the distance AP. Find the linear speed of the point P after a time pi L upon 3 V naught after the collision. Right. So it is given a rod. You can say uniform rod given mass, length, surface, horizontal and frictionless. Okay. Let us see how to start the problem. Right, first make a diagram for the given data. Rod AB. Rod AB, length L, mass M. Length L, mass is M. Let us take, so what is given? A particle of mass M hits the end A. Okay. Let us take this is end A and this is B. Hits now end A. Mass smaller, velocity V naught. Hits the end A, direction perpendicular to AB. Collision is elastic. After the collision, particle comes to rest. Now see what happens. In earlier lecture, I have discussed that if particle not sticking to rod, then rod rotates about its own axis. That means about center of the rod. That means we have to conserve angular momentum about center of the rod. Okay. Right. Let us see first what we have to calculate in this ratio m upon m. Right. First of all, focus the possible equations. Since it is now smooth surface on the system, net force equal to 0. So first I'm writing LCM. It is law of conservation of moment. Okay. So m into V naught is equal to, after collision, particle comes to rest. Now it is moving. This is now VCM at the same time. Since it is not hitting at the center, it is having rotation also. Rotation will be now anti-clockwise. And let us call this as omega. So now rod is having translation and rotation. Okay. So take now LCM, m V naught equal to m into VC. Then directly from here, m V naught by capital M, that is VC. Right. Next, now consider law of conservation of angular momentum, because on the system net torque equal to 0, right? See what I can write here. Since rod is rotating about center of the rod, so we conserve angular momentum about same axis. So it is m v naught L by 2. That is equal to, now particle comes to rest. So it is having now, so we are taking about this axis. So about center of the rod, because of translation, there is no angular momentum. It is only because of rotation. That is equal to I omega and I value ml square by 12 and omega, which we have to calculate. So from this, we get the value of omega. See how much? Omega will be, see what we can cancel here. L cancels 2, 6 times 6 m v naught upon ml. Okay, right. Now see what else we can do here. We want to find out ratio of their masses. First thing, small m upon capital M, how much? See, condition given that it is elastic collision. Okay. So elastic collision means kinetic energy for system before collision and after collision must be the same. Okay. So I can write here half m v naught square is equal kinetic energy after collision, that is half into capital M into VCM square plus half I omega square. So we know VCM and we know omega value, substituting values in that. This is one way of solving the problem. The second way is, since collision elastic, E value is 1. Okay. Then say what I can say here. When we are writing velocity of approach and velocity of separation, we have to focus with which point the particle is making collision. It is now making collision with one end. So focus now only this point. Okay. So for this point before collision, velocity is 0. Therefore, velocity of approach, it is V naught. That is equal to. Next, velocity of separation. After collision, this comes to rest, right? Now see for this point velocity. Because of translation VCM, because of translation VCM, because of rotation, this point follows circular path. So because of rotation, for this point velocity will be again right side. So plus r omega. R is now L by 2. L by 2 omega. So I have written here velocity of approach is equal to velocity of separation. Okay. That means I'm equating the modulus values. Now substitute values in this. V naught is equal to VCM. M V naught upon capital M plus L by 2. In the place of omega, 6 m v naught 6 m v naught upon 6 m naught upon ml, right? Okay. ml. Now see calculation. See what we are going to get. Throughout v naught gets cancelled. V naught gets cancelled. L, L cancelled. 2, 3 times m and m. So I can take m here. So m equal to m plus 3m. It is a 4. So ratio how much? It is equal to small m by capital M 1 by 4. Right? So we got the first one. Now focus the next one. Point P on the rod is at rest immediately after collision. Okay. So first of all, focus here. Where this point P, okay, this is A, this is center, and this is, you can see that point must be in between B and C. See why it is like that. Because of translation for each and every point, velocity VCM right side. Because of rotation, You can see for points in between B and C, velocity will be left side. I am repeating, because of rotation for points in between B and C, velocity will be left side. That means there is a chance of cancelling velocity because of rotation and because of translation. Okay. So the possibility is that VCM velocity because of translation that should be balanced by velocity because of rotation if distance equal to x. So x into omega. Omega value 6 m v naught upon m l. VCM. See how much VCM? It is m v naught upon capital M, that is equal to x into 6 m v naught by ml. Right? Now remain just calculation part. Then see what we get. M V naught gets cancelled. M gets cancelled. X equal to L upon 6. This is now distance from center, but we have to calculate from A. Okay, that means AP value. It is AP value L by 2 plus L by 6. That is our answer, right? Next, see what else. So next, what else? So this is how much? Simplifies. This is 2L by 3. Okay. Next question in that. Find the linear speed of the point P after a time given pi L upon 3 V naught after the collision. Right? We have to focus carefully for point P. Velocity because of translation, that is VCM, because of rotation or omega. Okay? Because of rotation or omega. So here what we got condition, VCM equal to R omega, right? Now we have to focus between those two vectors. What is angle? I am repeating. Already we have seen VCM is cancelled by R omega. So both numerical values are same. Now we have to focus between these two vectors. What is angle? Let me calculate theta. By what angle this rod rotates? Theta equal to omega. Omega value 6 m v naught upon ml. Theta equal to omega t. T value given pi L upon 3 v naught. Right? Now simplify this. What we can cancel? V naught 3 here 2 times L cancel. This is 2 pi, remaining is m upon m. And this value we got 1 by 4. This is now pi by 2. That means now rod rotates by an angle pi by 2. That means now rod will be like this. Right? Rotates by 90. So this end is B and this end is C. Okay. So for point P, because of rotation, velocity will be like this, and because of translation, velocity like this. Between these two angles now 90. See carefully. VCM that remains the same, right side. So VCM right side. Because of rotation, when rod rotates by 90 for this point, velocity will be like this. So angle is 90. That means velocity of point P, it will be root 2 times VCM, because R omega equal to VCM. Angle is 90. So root 2 VCM. Okay. So here you have to focus how we have taken coefficient of restitution. Okay. If you are knowing that, remaining is very simple. We are just focusing with which point it collides. Only for that point and colliding particle, velocity of approach and velocity of separation. Right? See next one. Two small balls A and B, each of mass m, are joined rigidly by a light horizontal rod of length N. The rod is clamped at the center in such a way that it can rotate freely about a vertical axis through its center. The system is rotated with an angular speed omega about the axis. A particle P of mass m kept at rest sticks to the ball A as the ball collides. Find the new angular speed of the rod. Okay, see how to solve it. So condition is given that we are having 2 point masses. See the question once small balls connecting by light rod. Okay, it is light. So it is now light rod connecting two small balls, M and M. Okay, clamp at the center. It is now rotating, maybe clockwise or maybe anti-clockwise. It is our choice. And given it is omega. Now one ball collides with a stationary particle and that is now sticking to that. Okay. Suppose when it is rotating like this, say 1 point mass here very close to this sticks to that. Okay. So here we can write law of conservation of angular momentum before collision. You can see I omega, I value m L by 2 whole square because total length is a into 2 for two particles I omega. This is equal to after collision. See where change comes now. After collision, this becomes now 2m. So this becomes now 3m into L by 2 whole square omega dash, which we have to calculate. Right? Now directly you can say m L by 2 whole square m L by 2 whole square. So omega dash is equal to 2 omega by 3. So very simple and direct. Okay. See next one. Two small balls A and B, each of mass m, are joined rigidly to the ends of a light rod of length L as shown. The system translates on a frictionless horizontal surface with a velocity v0 in a direction perpendicular to the rod. A particle P of mass m kept at rest on the surface sticks to the ball A as the ball collides with it. Find the linear speeds of the balls A and B after the collision. The velocity of center of mass of the system A plus B plus P and the angular speed of the system about C after the collision, omega value, and a hint is given here. The light rod will exert a force on the ball B only along its length. See carefully. See how we are solving the problem. So condition given that it is again light rod, again light rod, and given now 2 point masses A and B, two small balls. Two small balls A and B. And they have velocities V naught. And this also V naught, right? This is A and this is B. And given length equal to L. Next, a particle P of mass m kept at rest on the surface sticks to ball A. There is 1 point mass P having same mass. So when rod moves like this, A makes collision with this one. And given that it sticks to that, that means see now what happens. Initially M and M. Now it becomes mass 2m. I'm making diagram once again. Now this becomes 2m and this is m. If you observe the hint given, light rod will exert a force on ball B only along its length. So along the length only it exerts a force. Do one thing, let us take this is x-axis and rod is along y-axis. That means now rod exert a force on B along y-axis. Means on B along x-axis no force is acting. That means for B there is no change in momentum along x-axis. That means even after collision for B velocity V naught remains the same. But coming to this one, if you observe momentum equation m V naught, now this is m into V. Writing momentum equation m V naught, that is equal to, it is 2m into V. Then V value how much? This is V naught by 2, right? And once we get velocities for 2 points, and we know separation, right? Earlier we have learned that if we know velocities for 2 points in a rigid body, then relative velocity normal to line joining them upon separation gives omega. That means omega equal to relative velocity, that is V naught by 2 upon separation between them, right? So this is what giving us omega value. Okay.